Welcome! Today, we'll be tackling LeetCode problem number 1531, titled String Compression 2. This is a fascinating problem that challenges our understanding of string manipulation and optimization techniques. Stick around to explore different approaches and master this concept. Let's dive in. In this problem, you're given a string s and an integer k, and your task is to compress the string in a way that minimizes the length of the compressed version. However, you are allowed to remove up to k characters to achieve this. The compression process works like this: for any group of consecutive repeating characters, you compress them into a single character followed by the count of repetitions. If the count is 1, you omit it entirely. For instance, the string apt becomes a 3bc3d because the group of 3as is reduced to a 3, the b stands alone since there's only one, and the group of 3cs is represented as c3. Similarly, the string abcap compresses to a 2b2c3, because each consecutive group is replaced by the character and its count. The input includes the string s and the integer k, where the length of s can range from 1 to 100. The output is an integer, which represents the length of the shortest possible compressed string after removing up to k characters. The goal is to strategically decide which characters to remove so that the compressed result is as short as possible. For example, let's consider the input s equals apt and k equals 2. The output here is 4. To achieve this, we can remove two characters, the b and one of the cs. This gives us the string aac. When we compress this string, it becomes a 3c3, which has a length of 4. This is the shortest possible compressed length for this input. Here's another example: if the input is s equals abba and k equals 2, you can think about which two characters to remove to minimize the compressed length. In the case of s equals abba and k equals 2, the output is 2. By removing both b characters, the string becomes AAAA. When compressed, this results in A4, which has a length of 2. Now, let's look at another example: if s equals abc and k equals 2. Here, we need to decide which two characters to remove to achieve the shortest compressed length. For the input s equals abc and k equals 2, the output is 1. By removing the characters b and c, we're left with the string a. The compressed version of this string is simply a, which has a length of 1. This illustrates how the problem can vary based on the input string and the value of k. The constraints ensure that the string length will be between 1 and 100, and k can range from 0 to the length of the string. Additionally, the string will only contain lowercase English letters. As you approach this problem, consider edge cases such as when no characters can be removed, when the entire string can be removed, or when the string has no repeating characters. Another scenario is when the string consists entirely of one repeating character. By carefully analyzing the string and using a dynamic programming approach, you can efficiently determine which characters to remove to minimize the compressed length. To start, one natural way to approach this problem is to try a brute force method. The intuition here is simple: we explore every single way of removing up to k characters from the string, and then compress each resulting string to determine which one gives the smallest compressed length. The compression itself relies on counting consecutive characters and encoding their frequency. For example, the substring AAA would compress to A3. The steps for this approach involve generating all possible strings by removing k characters, applying the compression algorithm to each string, and finally returning the smallest compressed length among all possibilities. However, the computational cost of this approach is extremely high. Generating all subsets of deletions involves combinations, which grow exponentially with k, and for each subset, we still need to compress the string. This results in a total complexity of n to the power of k asterisk n, making the brute force method infeasible for larger strings, particularly when n can reach up to 100. The trade-off here is that while this approach is conceptually simple, it sacrifices efficiency entirely, making it impractical for real-world use cases. Now, to address the limitations of brute force, we can consider a dynamic programming approach that systematically evaluates the optimal compressed length while selectively removing up to k characters. The intuition behind this approach relies on the idea that compression benefits stem from character frequencies. For instance, a long sequence like AAA compresses to A5. Removing specific characters can reduce transitions between groups in the string, resulting in better compression. This problem exhibits overlapping subproblems, making it suitable for dynamic programming. The key is to define a state dp I, k, that represents the minimum compressed length achievable starting at index I with up to k deletions remaining. From each state, we have two main options: either keep the current character, which can extend an existing group or start a new one, or delete the current character, which reduces the number of deletions left. Additionally, a helper function is used to calculate the compressed length of any group. The base case is straightforward. If we process the entire string, the result is 0 since no characters remain. Finally, the solution is found by evaluating dp 0, k. This structured approach avoids trying every possible combination, making it much more efficient. In terms of complexity, the dynamic programming approach significantly improves efficiency compared to brute force. The total number of dp states is proportional to O, n asterisk k, as we need to consider every index I and every possible count of remaining deletions. For each state, the transition calculations involve evaluating options to either keep or delete characters, which takes O, n, time in the worst case. This brings the total complexity to O, n squared asterisk k. While this is still computationally expensive for large values of k, it is far more feasible than the exponential time required by the brute force approach. The trade-off here is that while this method is much faster, it can still pose challenges for edge cases where both n and k are large. Despite this, the DP approach strikes a good balance between practical performance and accuracy, making it a strong choice for solving this problem. The chosen strategy for this problem is the optimized dynamic programming approach with careful frequency management. The brute force method, while straightforward, is simply impractical due to its exponential complexity. On the other hand, the DP approach leverages overlapping subproblems and the optimal substructure of this problem, making it far more computationally feasible. A key insight that drives this method is understanding that compression primarily depends on group sizes. By focusing on transitions between groups instead of evaluating every character individually, we drastically reduce the search space. This was the pivotal realization that allowed us to optimize the DP approach further. However, it's important to note the trade-offs. For edge cases with high K, the state space still grows considerably, and while further optimizations such as using greedy heuristics might be possible, they could compromise accuracy. In summary, the optimized DP approach offers the best balance between correctness and efficiency, making it the most practical solution for string compression with deletions. In this problem, we aim to minimize the length of a string after compression, specifically when we are allowed to remove exactly k characters from the string. The compressed form of a string is created using run-length encoding, where consecutive characters are represented by their count. For example, the string A becomes A3B2. To solve this, we start by understanding the input and output requirements. The input consists of a string S of length n and an integer k, representing the number of characters we can remove. The goal is to return the smallest possible length of the compressed string under these constraints. Initially, we can consider a brute force approach. This involves generating all possible strings by removing k characters in every combination. For each resulting string, we calculate its compressed length using run-length encoding and track the minimum length observed. However, this is computationally expensive since the number of combinations grows exponentially with n. To address the inefficiency, we turn to a dynamic programming approach. Here, the key idea is to divide the problem into subproblems, reusing solutions to overlapping subproblems and avoiding redundant computations. This allows us to handle larger input sizes, up to the maximum constraint of n equals 100. To formalize the dynamic programming approach, we define a DP table where DP, I, j, represents the minimum compressed length of the first I characters of the string, given that exactly j characters have been removed. For the base cases, if there are no characters to consider, DP 0, 0 is 0 since there's nothing to compress. On the other hand, if we try to remove characters from an empty string, the result is invalid, so DP 0, j is set to infinity for all j greater than 0. The transition function is the core of the algorithm. For each character position I, we consider two main scenarios. First, we can skip the current character by removing it, which decreases the number of allowed removals j by 1. This updates DP, I, j, to the value of DP, I1, j1. Second, we can keep the current character, in which case we need to account for its contribution to the compressed length. This involves compressing it with the previous group of characters, adjusting the length based on the size of the group. By systematically evaluating these two cases for all positions and removals, we compute the minimum compressed length for every possible combination of I and j. Once we've filled the DP table, the solution to the problem is found in DP, n, k, which represents the minimum compressed length of the entire string after removing exactly k characters. To understand why this approach is efficient, we rely on key insights such as the mechanics of run length encoding. When compressing groups of characters, the contribution to the compressed length depends on the size of the group. Single characters add 1 to the length, while larger groups add 1 for the character itself and additional digits for the count, calculated as floor, log_10, count, plus 1. This means that the compression benefit increases with larger groups. The dynamic programming approach is efficient because it reduces the time complexity from an exponential O(2 to the power of n) to O(n squared asterisk k) by systematically solving subproblems and avoiding redundant calculations. Additionally, it handles edge cases seamlessly. For instance, removing all characters, k equals n, results in an empty string with 0 length, while no removals, k equals 0, means we directly compress the original string. Strings without consecutive characters are also naturally handled since their compression doesn't reduce the length. To implement this algorithm, we rely on a few key data structures. First, the DP table itself is a 2D array DP, I, j, used to store the minimum compressed length for the first I characters with j removals. To assist with run length encoding, we use auxiliary arrays that track the frequency of each group of consecutive characters. This helps us efficiently calculate the contribution of each group to the compressed length. Several optimizations can further improve the algorithm. For instance, by maintaining cumulative counts of character groups, we avoid recomputing character frequencies repeatedly. Pruning invalid states where j greater than k ensures that we don't explore unnecessary paths. Additionally, we can reduce the space complexity of the DP table from O(n*k) to O(k) by using rolling arrays, which only store the current and previous rows of the table. These optimizations make the algorithm not only correct but also practical for large input sizes, ensuring it performs efficiently within the problem's constraints. Here, we start by importing the ru_cache decorator from the functools module. This will help us optimize the recursive function by caching its results. Next, we define a helper function called get_length that calculates the number of characters required to represent the compressed version of a substring, based on its count. For example, if the count is 0, the output is 0 since the character doesn't appear at all. If the count is 1, only the character itself is needed, so the length is 1. For counts less than 10, we need 2 characters, the letter and the count, while counts less than 100 require 3 characters, and so on. Then, we define the main class solution and its method getLengthOfOptimal compression, which takes the input string s and an integer k, representing the maximum number of deletions allowed. Within this method, we calculate the length of the string s and define a dynamic programming function dp using the ru_cache decorator. This function takes 4 arguments: the current index, the previous character prev_char, the count of the previous character prev_count, and the remaining deletions rem. If the remaining deletions are negative, we return infinity since it's an invalid case. If the index reaches the end of the string, the result is the length of the compressed form of the last character group, calculated using get_length. The first option we consider is deleting the current character, so we make a recursive call to dp with the index increment by 1, the previous character unchanged, the count unchanged, and the remaining deletions decreased by 1. Finally, we handle the case where the current character matches the previous one. In this scenario, if the current character is the same as the previous character, we choose to keep it. This means we increment the count for the previous character group and make a recursive call to dp, advancing the index, keeping the same previous character, increasing the prev_count by 1, and leaving the remaining deletions unchanged. On the other hand, if the current character is different from the previous one, we close off the previous character group by adding its compressed length, calculated using the get_length function, to the result of a recursive call. In this recursive call, the index advances, the prev_char is updated to the current character, and the prev_count is reset to 1. The remaining deletions remain unchanged. At the end of this step, we return the minimum of the two options, deleting the current character or keeping it. Finally, the method returns the result of the dp function starting from the beginning of the string, with an empty previous character, a count of 0, and k deletions allowed. This implementation efficiently explores all possibilities using recursion and memoization to minimize the length of the compressed string after at most k deletions. Here, we begin by defining the getLength method, which calculates the length of a compressed segment based on its frequency. If the count is 0, it contributes nothing to the length. A count of 1 adds a single character, while counts under 10, 100, or more determine how many digits are added to the compressed representation. This method will be crucial for calculating the optimal compressed length later. Next, we introduce the getLengthOfOptimal compression method, which takes the input string s and an integer k, representing the maximum number of deletions allowed. Inside this method, we initialize a 4D dynamic programming array dp to store intermediate results. The dimensions represent the current index in the string, the previous character, its count, and the remaining deletions. Finally, we call the helper method, which is designed to recursively evaluate the optimal compression length. The helper method begins by handling two base cases. If the remaining deletions drop below 0, we return a very large value to indicate infeasibility. If we reach the end of the string, the length of the last segment is calculated using getLength. Additionally, we check if the current state has been computed before using the dp array to avoid redundant calculations. The first option we explore is deleting the current character, which reduces the remaining deletion count by 1 and moves to the next index. Now we consider the second option, keeping the current character. If the current character matches the previous one, its count simply increments, and we proceed to the next index. Otherwise, we calculate the length contribution of the previous segment using getLength and treat the current character as the start of a new segment with a count of 1. The result of the helper method is then stored in the dp array as the minimum of the two options, deleting or keeping the character. This ensures that we are always working towards the optimal solution while avoiding redundant calculations through memoization. By combining these recursive choices and utilizing dynamic programming, the algorithm efficiently explores all possible ways to compress the string within the given constraints. To solve this problem, we start with the input string s equals apt and are allowed to delete up to k equals 2 characters. Our objective is to minimize the length of the compressed string after making these deletions. Compression involves encoding consecutive characters as their count next to the character, such as AAA becoming A3. To achieve this, we use a recursive dynamic programming function named dp. This function tracks 4 key parameters: the current index in the string, the previous character in the compressed result, the count of its consecutive occurrences, and the remaining deletions allowed. By systematically exploring all possible character deletions and compressions, we aim to determine the optimal solution for minimizing the compressed string length. We begin the recursive process with index equals 0, prev_char equals, prev_count equals 0, and rem equals 2. At the first character, s0 equals a, we have two choices: delete this character, which reduces the remaining deletions to 1 and calls dp 1 0 1, or keep it, which updates the previous character to a, sets its count to 1, and calls dp 1 1 2. As we progress, consecutive occurrences of a at s1 and s2 increment the count to 3. When we encounter s3 equals b, the segment AAA is finalized with a compressed length of 2, and the process resets for the next segment. This logic continues for the following characters, deciding whether to delete or keep each one to achieve the smallest possible compressed length. After processing all segments, the optimal compressed result is A3BC3, which has a total length of 5. Now consider a second example with the input string s equals abba and k equals 2. The goal remains the same: minimize the length of the compressed string after deleting up to 2 characters. Starting with index equals 0, prev_char equals, prev_count equals 0, and rem equals 2, we analyze the first 2 as. Here, we can delete 1a, resulting in a call to dp 2 1 1, or keep both as, resulting in dp 2 2 2. Moving to the next segment bb, we finalize the compressed length of AA as 2 and repeat the same logic for BS. Finally, we handle the last segment AA. The optimal strategy is to delete 1A and 1B, resulting in the compressed string A2B1A1 with a total length of 5. For the third example, the input is S equals ABCDEFGH with K equals 3. Since all characters are unique, no compression occurs unless we delete some of them. Starting with index equals 0, prev_char equals, prev_count equals 0, and rem equals 3, we process each character individually. Here, the optimal approach is to delete the first 3 characters, A, B, and C, which uses all the allowed deletions. The remaining characters, D, E, F, G, and H, are kept, each contributing a segment of the form character plus 1. This results in the compressed string D1E1F1G1H1 with a total length of 10. In this problem, we use dynamic programming with memoization to determine the minimum length of a compressed string after up to k deletions. To analyze the time complexity, we start by examining the recursive function dp, index, prev_char, prev_count, rem. This function has 4 parameters. The index parameter can take values from 0 to n, where n is the length of the string, giving us n possibilities. The prev_char parameter represents the previous character in the sequence, which can be one of 26 lowercase letters or an empty value, making this effectively 1. The prev_count parameter tracks the count of consecutive characters, which cannot exceed the length of the string, so there are n possibilities. Finally, rem, which represents the remaining deletions, can vary from 0 to k, resulting in k possibilities. When we combine these, the total number of unique states in our memoization table is n*1*n*k, or equivalently, n²*k. For each of these states, we perform 2 key operations. One involves deleting the current character, and the other involves deciding whether to extend the current group or start a new one. These operations require constant work, or 1, per state. With the cost per state being 1, we can now determine the overall time complexity. Since we have n²*k unique states and 1 work per state, the total time complexity becomes n²*k. Moving on to space complexity, the primary contributor is the memoization table, which stores results for all n²*k states. Each state requires 1 memory, so the overall space usage for the table is n²*k. Additionally, the recursive call stack contributes to the space complexity. At most, the recursion depth matches the length of the string, or n, and each call uses 1 space. Lastly, auxiliary space is minimal, with functions like get_length and other local variables requiring only 1 space. When we combine the memoization table and recursive stack, the total space complexity becomes n²*k, dominated by the table. When comparing approaches, the dynamic programming method stands out for its efficiency. A naive approach would involve generating all possible strings by deleting up to k characters. With each character being either included or excluded, there are 2 to the power of n combinations. Compressing each string takes n time, leading to an overall time complexity of 2 to the power of n*n, which grows exponentially and is impractical for larger inputs. In contrast, the dynamic programming approach uses memoization to avoid redundant computations. It focuses on solving only the necessary subproblems, reducing the exponential complexity to a much more manageable n²*k. By limiting the problem space and leveraging previously computed results, this method provides a dramatic improvement in efficiency. The time complexity of the dynamic programming approach can vary depending on the constraints. In the best-case scenario, where k equals 0 and no deletions are allowed, the complexity reduces to n², as there is only one value for rem. For average cases, with moderate values of k, the complexity remains n²*k. In the worst case, where k approaches n, allowing the maximum possible deletions, the number of states is maximized, but the complexity still remains n²*k. In conclusion, this dynamic programming solution transforms an otherwise exponential problem into one with polynomial time complexity. With n²*k time and space requirements, the approach is both efficient and feasible for typical problem constraints, offering a far superior alternative to brute force methods. One of the most common mistakes in this problem is not accounting for edge cases. For example, if the string is empty or if the number of deletions, k, exceeds the length of the string, your solution might fail or produce incorrect results. To fix this, always validate the input up front. If k is greater than or equal to the string length, the answer is straightforward: you can remove the entire string, resulting in a compressed length of 0. Another frequent issue arises from inefficient brute force iterations. Trying to generate every possible combination of k deletions leads to an exponential number of possibilities, which quickly becomes impractical as the string grows longer. Instead, you should focus on optimized techniques like dynamic programming or sliding windows to reduce the computational complexity. Lastly, errors in the string compression logic itself are surprisingly common. For instance, you might miscount consecutive characters or mishandle single character groups. To avoid this, carefully simulate the compression process for test cases, such as AABC, where the correct compressed form is A4B2C1. This ensures your logic is solid. Another potential pitfall is overlooking the order of deletions. Randomly removing k characters without analyzing their impact on the compressed result can lead to suboptimal solutions. A better approach is to prioritize removing the characters that have the most significant impact on reducing the compression length. This can be determined by analyzing their frequencies or positions in the string. Additionally, space complexity is an important consideration. Allocating excessive memory for intermediate results, such as in recursive solutions, can cause memory limit issues, particularly in competitive programming scenarios. To address this, aim for in-place modifications whenever possible or carefully manage memory usage in recursive approaches. From an interview perspective, there are a few key insights to keep in mind. First, recognizing patterns in the problem is crucial. Many problems involving string compression, deletions, or modifications can be reduced to dynamic programming or greedy algorithms. Identifying this early can save you valuable time. Pre-processing the string is another powerful strategy. By grouping consecutive characters up front, you can often simplify the problem and avoid redundant computations later. Additionally, consider whether the problem exhibits optimal substructure or overlapping subproblems, which are hallmarks of dynamic programming. Balancing time and space complexity is another important trade-off to consider. For example, while dynamic programming solutions are usually faster, they might consume more memory. Finally, exploring related problems can help you spot similarities and improve your understanding. Examples include LeetCode 443 for basic string compression, LeetCode 767 for reorganizing strings, and LeetCode 1405 for constructing strings under specific constraints. When it comes to alternative approaches, the greedy strategy is often a good starting point. This involves removing the characters that contribute the least to the compression length. While this method is faster and easier to implement, it doesn't always guarantee the optimal solution. Dynamic programming, on the other hand, is a more rigorous approach. By using a 2D DP table, where each entry represents the minimum compressed length for a specific range of characters and number of deletions, you can ensure optimality. However, this comes at the cost of higher space complexity. Another option is the sliding window technique, which uses a fixed-size window to evaluate the impact of removing k characters. This approach is simpler and more intuitive but might not work for all problem variations. Each method has its trade-offs, so understanding their strengths and limitations is key to selecting the right one for a given scenario. Great job! We've completed our exploration of string compression 2. This problem tested our ability to optimize string manipulation, a valuable skill in both interviews and real-world coding scenarios. Remember to keep practicing and applying these strategies. Thanks for watching, and I'll see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!